Mr. B. Dhanasekar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We are having the subject theory of the compiler design, and as far as this episode is concerned, we will be having the topic called finite automata. So, in the previous episode we have seen the regular expressions, so how the regular expressions are formed, and we know the advantage of regular expression is for describing the token structures available in a programming language, which will be required for the first phase of the compilation, that is lexical analysis, and the output of those, that is the lexical analysis phase, that is the tokens, will be given as input for the parser, and the parser will in turn that will take care of the statement formation by aggregating the various tokens available in your source program or which are returned by the lexical analyzer. Now, the question is, how will you go for the implementation of a lexical analyzer? Regular expressions are there, they will be only the non-procedural representation of the token structures, but they should be converted into some programs, that is having that is the list of regular expressions. If they are not converted into proper programs, then it cannot be used for recognizing tokens. So, every regular expression which is there in the non-procedural format should be transformed into a procedural format. So, in the meantime, that is in between your regular expression and the program, we have one important tool called finite automata, which will be really helpful for us in designing the lexical analyzers from the non-procedural format, and these finite automata will be transformed into its equivalent program, which will be a procedural format. So, just to make the process much easier, that is to design or to make the design of the lexical analyzer much easier, we go for introducing the tool called finite automata. So, they are simply looking like the transition diagrams, which are having both states and transitions. Normally, the transition diagrams are having states as well as transitions, and as far as the states are concerned, there is one special state which we call it as the start state, and where the system is initially placed, that is every transition or every recognition of string should start only from the start state, but from the start state we will keep on recognizing tokens, recognizing symbols based on the various transitions available in the edges or the transitions, and it is required to have one or more number of accepting states also. So, it can be like suppose if you are reaching one of the accepting state, the meaning is a token has been recognized. So, if you can't reach the accepting state, or if you find that after reaching the accepting state also there are more number of symbols available which cannot be further processed, in that case it is going to denote the failure of recognizing a valid token. But as far as the finite automata is concerned, if you reach the final state, it will immediately report a token to the parser in the form of a pair, which will be what is the type of the token and what is going to be the exact lexeme. So, that if it is going to be an identifier, some installation of that particular identifier into the symbol table will be done, or if it is an operator, it will be checked against whether it is going to be the right operator or not. So, that is going to be the aftermath of the recognition of the tokens, but here the finite automata will be used as a tool for recognizing or identifying the tokens. So, we have start state and we have final states or accepting states, and if any pattern with the start state, if you are able to reach the final state of the automata, then we can claim that a token has been successfully recognized. If not, the token is not successfully recognized. So, that is the advantage of going for the finite automaton. So, as far as the accepting states are concerned, there will be some specific code being associated with that, and that code will do the activities to be carried out on reaching or on recognizing a token. So, if the final state has been reached, then we can say that the string has been accepted, or we have a valid token which will be returned to the parser. And as far as these finite automaton are concerned, there are two important types. One is going to be the deterministic version, and another one is going to be the non-deterministic version. So, what happens here is we have a state, and from there may be one or more number of transitions, and if the transitions are unique, like for example, from the state that is 1 for a symbol A, if exactly only one state will be the resulting state, then what will happen is the behavior of the finite automaton is called deterministic. But if it is possible to traverse or reach more than a state from the current state for the same symbol, then we will be having a non-deterministic behavior there. So, that we will not be able to clearly say what will be the next state from where we have to resume the that is the recognition process. But when you are having a deterministic finite automaton, what is the reason for going into a non-deterministic finite automaton? It is simple reason. The simple reason is we will find it easy to come up with a non-deterministic finite automaton from the regular expression, which is a procedural non-procedural representation, and once we know the NFA has been obtained, that is your non-deterministic finite automata has been obtained, then we have an algorithm called the subset construction algorithm. So, which will transform the non-deterministic finite automaton into its equivalent deterministic version. But once the deterministic version has been obtained, that can be very easily transformed into a program in C or C++. So, now we have the compiler for transforming a C program or C++ program, so that we will be able to find out the object version of the program, and the object version once it is executed, it will read a source program given for A, which is supposed to be translated, and from that we will find out the stream of tokens. This is the actual flow being happening as far as the design of a lexical analyzer is concerned. So, here we should know that is what is the meaning of deterministic version and the non-deterministic version. We have an example of a simple finite automaton. So, wherever we are having circle, they are actually called states. So, this is an example of finite automaton which will recognize the comments from C++ programs as well as from C programs. We know these C++ program comments are coming up with two number of slashes, continuous slashes, then followed by whatever is there, it will be considered as a comment in your C++ programming language. And the same thing, if it is going to be in C program, we wanted to have a slash followed by an asterisk, then followed by anything whatever it is, and finally it should end up with an asterisk followed by a slash. So, here we find that when you reach none, it can be either considered as a no common state or a common state from C++ or a comment from C programming language. So, we find this is going to be a deterministic finite automata, because you see that is a slash which has only one outcome which reaches the state, and if you find further another slash, we will go for C++, and if it is a slash followed by an asterisk, we will go for C, and only if you find a star, we will jump from this particular state to another state called star, where once again it is possible to have multiple number of stars also, or if anything other than star is there, we will come back to here and continuously. The reason why we are having a different star here is we may have the command ending with one star followed by a slash, or we may have even multiple stars in the comment statement of that C program, followed by a star and followed by a slash. So, that is what we are having a star here, and if there is any more star, it will be continuously on the state, and then if anything is there, anything other than that is there, we will come back to C. So, this finite automaton will be capable of recognizing a command script. So, that is command line as far as any C program or even C++ program is concerned. The important things here we have to understand are, so what is the state and what is the transition and what is the label on the transition and what happens on seeing a label available on the transition from the input. So, it is going to change the state continuously for reading the symbols from the source program, and it will reach the next state, and as long as we are in non final states, we can claim that there is a progress in recognizing tokens, but once we have reached the final state of the automaton, we can say the token has been obtained. So, return the token to the appropriate place, maybe like the parser will receive the token, or we will do some installation onto the symbol table, so that the entries are made on the symbol table for the identifiers, or it will be checking for the operators or constants anything. So, that is what happening as far as finite automaton are concerned. So, now how the finite automata are represented in the memory. So, they are represented with the help of a transition table. A transition table is a one dimensional array of entries. So, where we will be having the transitions like that is what is going to be the source state and what is going to be the input symbols, they are available in the column wise, and the source states are available in the row wise, and for every state for different input symbols we will be having one entry on the column. So, if you want to find out the transition from a particular state, you go to that row and find out the appropriate column. So, we will be having some entry there, and that entry will tell you what is going to be the resulting state for that particular transition. As long as the automaton is going to be a deterministic finite automaton, there will be one entry available in each entry of each cell of the that is the transition table, and if it is going to be a non-deterministic version, then it is possible to have even more than one entry, so that we will be in multiple states at a time. So, here is a structure for the transition table. It is a tabular listing of the transition function. Rows are corresponding to the states and columns corresponding to inputs. So, what is the meaning of an entry in a row? So, it is if you are in the row called Q and a column called A, then the intersection that is Q comma A is going to be the resulting state from Q for the input symbol A. Suppose if you are having the transition function, we call it as del normally as a transition function. So, del of Q comma A is equal to P, then in the row called Q for the column called A, the entry available in the table, that is in the transition table, is going to be P. So, once again we will be having some entry for P, provided if there are transitions available from P. So, if you find a state from where there is no that is further transition, then we will say that the entries for that particular row or that particular state are going to be empty. So, we may have even that is a state as outcome, or sometimes there will not be any state as outcome, we will be calling it as null entry, which says that there is no transition from the current state for any input symbol. So, that is the meaning of that the transition table entries. So, it is not necessary that all the entries must be available or non-empty as far as the transition tables are concerned. It is fully depending upon what automata we are having and how the transitions are defined, whether there are transitions available or transitions are not available. So, we shall continue this after a short break. So, welcome back. We are studying the transition table representation of the finite automaton, that is deterministic finite automaton. I said that the rows are all corresponding to various states and columns corresponds to the various input symbols, and every entry in the table corresponds to the resulting state for some transition. So, here we have an example. So, the transition diagram is having 3 number of states q0, q1 and q2, and we find that q0 has 2 number of outgoing transitions. So, one for 0 and another for 1. So, if it is 0 it goes to that is q1, and if it is 1 it comes back to q0, and similarly from q1 if it is 0 it comes back to q1, and if it is 1 it goes to q2, and from q2 if it is 0 we are coming to q2, and if it is 1 also we are coming to q2. So, this diagrammatical representation could be transformed into a tabular representation, that is what here given, and two important things here we have to understand are what is the start state, first one, and the next one is going to be what is going to be the final state. So, in the case of transition diagrams, the start states are marked with a small incoming arrow which has no predecessor, and the final states are marked with double circles which are completely different from the other states. There may be more than one even final state also, but there is no point in having an automata which does not have a final state at all, then the language of that finite automata will be empty. So, the start state and the final states are referred by a small incoming arrow along, you can see here along with q naught, which is a small incoming arrow which says that q naught is start state, and we can find a small asterisk, a star kind of operator along with q2 which says that q2 is the final state. Then rest of the things are taken directly from the transition, there is a diagram, we can find q0 comma 0 is q1 and q0 comma 1 is going to be q0, q1 comma 0 it goes for q1, and q1 comma 1 it goes to q2, and from q2 all the transitions are coming back to the same state, that is what we are having q2 for the 0 and even q2 for 1 also. So, this is how the deterministic finite automata are represented in the transition table or tabular format. But when you go for a non-deterministic finite automaton, we will find that from a state for a particular symbol it is possible to have multiple states as output, which means that at any point of time during the recognition of a token or a pattern, the finite automata can be in more than one state at a time. So, then there should be some provision for storing more than one state in the table which we call as a transition table. So, here is a table available, the finite automaton and the corresponding table. So, we have a finite automaton which is non-deterministic, it is because of from q0 we find 2 number of resulting states obtained, one is q0 and another one is q1, but whereas from q1 is concerned it is deterministic behavior because there is exactly only one transition for 1 which goes to q2, and from q2 there is no outgoing transition at all. Actually this will recognize a set of all strings ending with 0 comma 1, but now you look at the representation, your transition table representation, we have 3 rows because 3 number of states are there, q0, q1 and q2, q0 is marked with an incoming arrow and q2 is marked with an asterisk. Then here you see that the column for 0 and the row for q0 has 2 number of entries, it is q0 comma q1. So, in general when you are writing the definition of a non-deterministic finite automata, so for a single state with a single input symbol, the output is going to be any one of the subset of the set of states available from the given set of states. So, for example, if you are having q1, q2, q3 are 3 states, so we know that there is going to be 8 possible outcomes. So, as a result of a transition for even a single symbol, the output is going to be either there is q1 or q2 or q3 or q0 q1, like all 8 possible combinations are there. So, that is what we put the output of the transition from a state for an input symbol in a non-deterministic finite automata in the set format. So, we find that q0 and q1 are written inside the set bracket. It is only because of a non-deterministic finite automata will give you more than one state as a result of applying a transition for a symbol A. That is what we call it as non-deterministic finite automata. So, now we need to understand that the language recognition power of a non-deterministic finite automaton and a deterministic finite automaton both are going to be same. That is, whatever be the set of all strings recognizable by a non-deterministic finite automaton will be recognizable by a deterministic finite automaton. Similarly, any string or any language that can be recognized by a deterministic finite automaton can also be recognized by a non-deterministic finite automaton, which means we will be having equivalence among the deterministic finite automaton and the non-deterministic finite automaton. So, given an NFA, it will be possible to transform it into its equivalent DFA, or we can even see a deterministic finite automaton as a non-deterministic finite automaton also. So, for every that is non-deterministic finite automaton, there will be an equivalent deterministic finite automaton. The transformation will be done by the subset construction algorithm, so which will construct the deterministic finite automata from the non-deterministic finite automata by constructing the resulting states from your non-deterministic finite automata. So, the resulting states must be for your deterministic finite automaton, but they are constructed from the set of states available in the non-deterministic finite automaton. So, what are all the possible states now we will be having in the deterministic finite automata will be, if there are n states available in the non-deterministic finite automaton, there will be at most 2 power n number of states in the equivalent deterministic finite automaton. The best case there will be exactly n number of states in the deterministic finite automaton, but in the worst case it will be 2 power n number of states possible. So, most of the time we will be having lesser number of states than 2 power n, because many of the states will not be reachable when you transform it into its equivalent deterministic finite automaton. Here is the conversion. You find that the given input is this one. So, q0, q1, q2 are the states, q0 is the start state and q2 is the final state. And now if you are starting with the q0, so what happens here is, for 0 we are having q0 comma q1, and for 1 we are having q1. So, now in this table, actually this is the table meant for deterministic finite automaton. q0, q1 will not be considered anymore as two different states, but will be considered as a single state. Similarly, q0 alone will be considered as a single state here. So, now from this particular stage and as well as from this stage, we have to construct the resulting transitions. So, we find q0, q1 is a state whose resulting transition for 0 is obtained by taking the transition from q0 as well as from q1. So, we know the q1 transition for 0 is empty. So, we will be still having q0, q1, and whereas 1 is concerned, we are having q0 and q2. So, q0 is obtained as the outcome of q0 comma 1, and q2 is obtained as a result of that is q1 comma 1. So, we will be having q0 and q1. So, you apply the transition for each state, that is both from q1, q0 and q1, then take the union form. And similarly, we are having q0, q2, that is going to be another state. So, so far we haven't evaluated the transition for that, and we find the transitions are going for q0, q1, and another one is going to that is q0, that is for the symbol that is 1. And we find that certain transitions are states are written in blue. So, those states cannot be reached from the starting state of the finite automata. That is, if I start from q0, I can go to q0, q1, or I can go to q0. So, q0 is the same state, otherwise we can go for q0, q1. So, q0, q1 now, and from q0, q1 I can either come back to q0, q1, or I can go to q0, q2, and from q0, q2 I can come back to q0, q1, which is a state already we have generated, or even Q0, that is also already generated. So, there is no point in thinking about Q1 Q2 or Q1 Q2 as a single state or Q0 Q1 Q2 as a single state. So, those states are unreachable states, or you can even claim them as dead states. So, now the question is, how will you find out the start state and the end state of your resulting automaton? The start state of the automaton is same as the start state of the NFA, but whereas the final state of the automaton, that is a deterministic finite automaton, will be the set of states which contain the final state of the NFA as a member. So, we have Q2, where Q2 is a member in the that is Q2 is a final state of the NFA, and another state is we are having Q0 Q2, that is also a final state, and Q1 Q2, that is also a final state because Q2 is a member, and the last one is Q0 Q1 Q2, that is also a final state because of Q2 is a member. But out of the 4 states, we are having only one reachable, that is Q0 Q2. So, we will be having only this as the final state of the automaton. So, this is what the resulting automaton. So, we have the first state, that is Q0, which has 2 transitions, one for 0 and another one for 1, but they are all going for unique states. One come back to that is Q0, another one is going to Q0 Q1, and this is another state from where we are having 2 transitions, one for 1 and one for 0. 0 comes back to the same state and 1 goes to Q0 Q2, and from Q0 Q2 once again we are having transitions for both 0 and 1. So, one is going to Q0 Q1 and another one is going for that is Q0. So, we find that the resulting transitions are all going to have that is unique states. So, this automata will become the deterministic version rather than the non-deterministic version. So, this is how we are converting a non-deterministic finite automaton into its equivalent deterministic finite automaton. To summarize, the definition of finite automaton has been studied, and the conversion from NFA to DFA has also been studied. The questions are, so we can have the definition of deterministic finite automaton, or the differentiation of DFA from NFA, and how the NFA that is designed from language specification, and another one is that is how the NFA are all transformed into deterministic finite automaton. These are the possible questions. So, with this I complete this episode of your lecture. Thank you.